Can I have a refund? Yes, we will refund people who didn't get their problems in. I might do like one more, I'm not sure, but I kind of have a mind to do IMO 19821 because it's an IMO 1, so I think it'll go by quickly. We'll find out real soon. Flamestorm. Yeah, if we don't get to your problem, I'll refund it at the end of the stream. Okay, so the heck? Okay. Okay, so actually, I'm curious. What was the format of USAMO in 1999? Was it still was it? Oh, it was actually 2 rounds by then. Okay. So this is actually supposed to not be an easy problem. It's supposed to. I bet you can still run it over. Like, because if I pick random P... Oh, that doesn't help. I was gonna say if we pick random P, the expected value is 2. But that's not gonna help us here. So, like, what's the shit? Like, they want A plus B and A plus C. Like, they want them to be negatives. Okay, that's fine. I can see how you do the 2 variable version of this. But that's so easy that it's unlikely to give me much insight. P divides A plus B plus C plus D suffices. Wait, yeah. So, okay, so apparently the statement is we definitely have R A plus B plus C plus D is 0 mod P, so we always have P divides A plus B plus C plus D. Right, the problem statement just implies this. And the thing that's exactly this problem is basically saying like I'm gonna abuse mod notation. AR mod P plus BR mod P. Oh crap. It's basically saying this thing is exactly 2P. For every R. Where the mod is the remainder because there's apparently just no good notation for it. I agree we can, without loss of generality, scale so that A equals 1 or D equals 1 or whatever. I just don't see the point though. We can scale that way. I just don't know if that's useful. Actually, maybe it is. Like, maybe if I should be thinking about size. So, like, if A equals 1 and then you take R equals 1, that means that C and D are both pretty large. Or something like that. That seems right, actually. That feels good. Okay, I agree that let's agree that A equals 1. And A less than B less than C less than D. And the idea is that, like, so at that point, okay, also, like, as we should, let's let them be strictly less than P. So, that means, like, 1 plus B plus C plus D is exactly equal to 2P. So, both of these, you know, you get some pretty nice size constraints here. Like, they're all really, they're pretty big. So what happens if I look at 2? When I double them, something's supposed to happen here. Here's a thought. I feel like for P, if you take 4 equations, oh, never mind. Never mind. I almost want to take floors or something like that. I almost think I should have taken floors to start. Okay, humor me for a moment. I'm gonna write the floors and see what happens, just 'cause I'm curious. I don't really expect it to work, but we've made a reduction where we think like a plus b plus c. I'm not even gonna use the one. It's like a plus b plus c plus d is equal to 2 beyond the dot, and also like fractional x is x minus floor x. So wait, what does that do? So it's like r for every r. Hang on. For every r, the statement is saying that r minus floor of RA over P I'm really confused. Something's wrong. What was the USAMO problem you're thinking that's similar to this? Might be 2003, 1 or something? Or it's not 2003. There's one about fractional parts. Let me just list them. $2006. It was probably 2006. Yeah, you're thinking 2006. Anyways, so the problem statement, if I translate it verbatim, is saying this, but when I take r equals 1, that means that this thing is actually equal to, this whole thing is equal to 2, right? So r equals 1, each of these disappears. We're taking as a standing assumption this is like 1. Okay. So the problem statement is equivalent to 2 2r minus 1 is equal to that. Okay. I don't know if that's actually any better. I was curious what the floor equation would say. For, yeah, any r. Okay, anyways, let me go back to like an actual, something that might actually work. So somehow when doubled, both C and D are bigger than P halves. Yeah, that's correct. C and D are both bigger than P halves. because otherwise, if D is less than P halves, this is way too small. If C is less than or equal to P halves, then it's still too small. Because if this is P halves and this is P halves, I guess this could be like P minus 1. Oh, but P is odd. Let me try like 7. If this is like 3, yeah, too big. So, okay, first equation already implies... this is a hard NT problem? Really? Oh, now I'm scared. No. So, first equation already implies... this already forces C and D to be larger than P over 2. Because otherwise, left hand side is too small. And if that's the case, then we have a good control over the next equation. The next equation, we actually know what it does to everything except B. This thing will be exactly 2C minus P, we regroup once. This thing will be exactly 2D minus P, we regroup once. So, and what does that do? This is 2B, possibly minus P or not. Alright, I'll abuse notation, right? This is like something. But in order for this to be correct, this must be 2B. So this means B is strictly less than P halves. I don't know if that's good for us. I guess they're on different sides of P halves. Well, I feel like if we repeat this argument, maybe I can keep pushing or something. Because the idea is I want to force it such that it regroups every... I'm trying to control the regrouping, right? Yeah, we want D equals P minus 1. We believe that A equals B equals 1 and C equals D equals P minus 1. So we want the C and D to always regroup and the B and... yeah. So in general, when I do 3 plus 3B plus 3C plus 3D, you know that 2 of them have to regroup. I really want them to be C and D. Is there a chance they can be... like basically, I'm interested in the regroups. Like A plus B plus C plus D equals 2P is definitely true. And then there's a regroup at D. If there's a regroup at C, there's a regroup at D. So is there a chance that D regroups, but C does not, and then B does? That seems pretty bad. Okay, I want to try something. I think this is the point where I want to draw a grid. Figure out what's going on. Can we try small values of P? I mean, I think small values of P don't tell you too much. But the basic premise, I think, is you have like I'll make a table like this: 1, B, C, D. I'll call this one 1, and it's like 2B, 2C, 2D, and then 3D, 3C, 3B. That's the way I want to think about it. You have a grid that looks like this. Let's go P minus 1, P minus 1B, P minus 1C, P minus 1D, and every number has regroups associated to it. Like at some points, the number will regroup, and the number of times it will regroup is exactly equal to the number minus 1. And you want to set it such that there's always exactly 2. So the equality case is when the regroups are all here, like there's never regrouping here and there's always regrouping here. If you have some other messed up number, basically at every point you want one number to regroup and the others to not. I think we should start setting x equals a plus b mod p because of the condition. I don't see what that was going to do for you. Like, just because the condition says that, I don't know, we could force p divides xyz or something. I don't believe that. Like, I feel like the reason the problem talks about a plus b is because the extraction is that, like, a equals minus c and b equals minus d, and that's why this is happening. Shoot. Oh wait, that's an equality case. Sorry. For some reason I thought... Oh crap, alright. Well, either way, like, the reason that, like, the problem talks about, like, this is because, like, what? That's... in the solution set, like, a equals minus d, b equals minus c, right? Like, the numbers themselves, a plus b, a plus c, don't seem like they're especially interesting? I don't know, like, I don't see why that number should matter. Alright, good night, Gecko Lizard. See ya. Brain is hurting. What does that make me, huh? Alright. Sorry, so there's another equality case where B regroups if and only if C doesn't, but I want to show that D always regroups. Without loss to generality the order of the variables, you think the answer would be fixed? I'm not sure what you mean by that. I mean... if anything, we definitely care about a plus d versus b plus c. But... Let me just draw an example. I think that I'm having a hard time thinking about this because I have no... this is too abstract. Let's do like 7 or something. B equals 7 cartoon. So this is the equality case, and where the regroups are happening like here, 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 and then here, 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 here. So this, maybe I didn't pick a great example. Maybe do I want it a little less? I want it a little less frequent. It's harder to see this way. Is it reasonable exactly one combination of x plus y always works? Yes. Yes. It's a equals minus d and b equals minus c. Like, that has to be it. Because we know that p divides that sum, and so, like... you know, they have to pair up 2 and 2. And because we ordered them, it has to be a, d, and b, c. So basically, I want to make sure that B and C can't ever regroup at the same time, and if I can do that, I'm set. So is there like ever a value of R? It's like B. This is a regroup, and this is a regroup, but this one is not. Is that possible? Is that ever just... Is that at all possible? Assuming that D has regrouped every time up until then. Like assume that... My feeling is that this shouldn't be possible. I'm not sure if it's gonna hold up. So what does it mean if if D regroups up to R but not R plus 1? That means that D is greater than... It's like D is greater than... I feel like this is going to not turn out well. That's what the... This condition is that... Alright, so... This feels like some fairy garbage or something. Feels like fairy stuff. I have that feeling. I don't know if that's going to help me at all. I suspect it won't. I should be looking at the fraction like D over P, right? That's a better frame. Okay, so meanwhile, what does it mean if C regroups and also B regroups? So if C regroups, that means there was an integer RC. It's like somehow there was a... What does that even mean? Yeah, that just means there's a multiple of P here, right? So there's a multiple... Okay. Take modulo P. So, is this some statement about fractions in... I feel like I should be able to construct a counterexample to my claim. Maybe? Maybe take r equals p minus 1. You don't get anything if you take r equals p minus 1. What happens when r equals 1? I kind of used up that information already by asserting that a plus b plus c plus d equals 2p, I think. I mean, I didn't use it that much, but... No, like, we have... d equals p minus 1 is definitely true. Like, if the problem is true and we assume a equals 1, then it follows that d equals p minus 1, and then b and c, b equals p minus c. That's what we're going after. And what I'm trying to do is, like, say, like... I'm looking at these regroups, right? And the claim is that there's a regroup every 2, exactly. And... I'm looking at the first place where D doesn't regroup. That's the place where B and C must both regroup. And so you get 3 inequalities. This is the inequality says that D regrouped for the first time here. Like D over P is very close to 1. But B and C both regroup. Thank you, Picky2244 for the follow. And I'm trying to see if that does anything, although I can't tell, honestly. Maybe I'll have an easier time thinking about this if I actually write out the whole thing for 7. So like when I look at where the regroups are, this has a regroup everywhere. This has a regroup there. This has a regroup here. So this is a regroup chart I'm drawing. And like the claim is that the only way to pick 2 such that that's weird. Hang on. I messed something up. Number of regroups is 1, 2, 3, 4, 5. And you want to pick it such that like every row is exactly 2 regroups. And the claims you can only do that using the 5 column. And if not, what goes wrong? I don't know. Hi, we're all bad at math. That's kind of how math be. Okay, so like, yeah, the claim I'm trying to prove, it doesn't look like it's... I was hoping there would be some stronger claim that's true, but it doesn't look like it. Shoot. K or K plus KX being above or below P? I mean, we already checked that, I don't know. We had a lead earlier where we showed that C and D were both at greater than P halves and B was less than P halves. We could keep pushing the, maybe? Yeah, maybe I should keep pushing that lead. So the first, like R equals 1, R equals 2 tells us C and D are greater than P halves, and B is strictly less than P halves. And then the next one, there's some more possible regrouping. If C regroups here, D also has to regroup, so B doesn't. So either C regroups, meaning C is CD greater than P thirds, 2P over 3. And so the regroup happened there. B is harder to say anything about actually. So actually, no, B is less than P halves. So for it to regroup, it's in the interval 1/3, 1/2. So either that B is less than P thirds, or D regroups, and C does not. B regroups, and C does not regroup. So this actually feels more promising. Let me switch back to here. Yeah, each of these, you're getting statements, and I think you can keep pushing them. Maybe you can keep pushing them? It feels more promising than the garbage I was doing. The other thing I was doing didn't feel very good. So I think you always have... Okay, I actually need a picture for this though. Back to board. So initially you have like B here and CD here. Then on the next step you take 1/3, and what you get is that B and C are still like symmetric, and then D is still at the far right. Like D is like on the far right. So in the case where, what's the case if B and C lie here, then when I hit the 1/4, again the same statement should be true, where B should regroup, or yeah, B and C will still be symmetric or something like that. So the case that's confusing is if B and C are both in this 1/3 blob, and that's where I need to bring in the 1/4. So there is some FAREY type thing. 3/4. Sorry, I need to scroll. Where's my mouse? So if B and C are both here, then when I consider quarters, what's the possibility? Well, actually, if they're between 1/3 and 1/2, there's no regrouping at all. Just if they're between a, yeah. So nothing happens. C must regroup, and D is still on the far right. Then at the next interval, I consider the fifths. Wherever the heck they are. Oh, FAREY. Is it really going to be FAREY? So I think the induction claim is that hang on, what am I doing? What am I doing? Something's wrong. The claim earlier was that if C regroups, then so does D, and that doesn't work once I hit the 5. Right, because if C was on, oh no. Like, why can't I have this picture where B is here, C is here, and then D is on here? What's the statement I'm trying to prove? What's the statement with the floors that I had? Yeah, now that I'm looking at it this way. It was like 2r minus 1 is equal to rb over. Right, so back when it was still in 1/2, it was still in halves. It's like 1 plus 1. That makes sense. And then when it was thirds, this checked out. It's like 1, 1, 2. Now 2, 5, 8 checks out, and I am in big trouble. I really didn't want that to check out. 1, 2, 3. Yeah, okay. So doesn't this feels like it should give me a counterexample to the problem or something. So the first time it doesn't behave symmetrically, it looks something like this, where D rounds in a way that's bad, and then B and C round in a way that's up. And if P was like not a prime thing, then I should, like, you could take a thing that constructs a counterexample. So I need to somehow rely on the fact that the next time, like by the time P is large enough for these differences to exist, you can find some other value that breaks it. And I don't know. So this is the case I'm worried about, isn't it? If I put BCD like in this picture, then I can get this thing to be true for r equals 1, 2, 3, 4 and not be in the right places. Or 1, 2, 3, 4, 5. 2, 3, 3. Yeah. 3, 3. Okay. So when this happens, I need some other value of r. I should find the first place where something bad like this happens, and I should take a value of r that will cause things to blow up. That is my plan. I don't see how I will do that. How do I do that? Hello. God. Yeah, this is actual number theory. Oh no. Is it midnight? Wow. I mean, maybe what I should do is I should just pick a large prime P and see why this causes problems. So the problem is I expect things to be too small. So I want to like take something. What do I do? Help. This is the bad picture. Wait, is 1/2 plus 2/3 plus 4/5 just straight up too small? So what is this sum equal to? 8/15ths plus a half. So like 30, no it's not. No it's not, that's big enough. No it's not, wait. 22/15ths, 44/30ths, 58/30ths. No, what? 22/15ths, 44/30ths, so 59/30. It's slightly smaller than 2, and this will cause problems if P is big enough. On the other hand, the existence of numbers in these intervals at all, like the fact that there is if there's a number, if there is any integer between 1/5 P and 2/5 P, that means that can I get a lower bound on P from that? So this will fail for all large enough P. I'm wondering if there exists any P at all where you can actually find numbers in these intervals. Well, so if there's an integer between 2/5 P and 1/2 P, can I say that P is like not too small? Probably, right? Maybe? Maybe not. Yeah, I was just thinking like if I wanted to keep proving that D was to the right of like 3/4, 4/5, 5/6, etc. And you take the first fraction for which that's not true, And well, I was doing some fairy stuff up before then to say that, you know, B and C were always, yeah. Yeah, I think this is... So if... Like, if I have a statement like 2/5 B is less than... B is less than P over 2. Like, where B is an integer. And that's clearly dumb nice, right? 10B is less than... I feel like the fact that they're adjacent fairy things should be telling me something, but I don't see what. I just think it's interesting that like a particular R thing will falsify it for a large enough P. The alternative is I can try to look for a different value of R to falsify it, like... Although R equals 6 will work fine because there's no... Will it work fine? Where is the 6's full? Here, 3, 5... 5, 6 is here, 3, 5... Oh, 6 is actually too small. If I drew that picture, then when I look at the 6's, the one right after it, 4, 6 is 2/3. That's over here. 4, 3, 2. Okay, so maybe I should just look at R plus 1 or something. Okay, well, it doesn't matter. Like 4, 3, 2 will falsify this. If I just look at... This picture can't happen because of just R equals 6. The next one won't be large enough. And that's sort of because 2/3 and 1/2 were already composite, so when they're in these intervals, they can't move out of those intervals. I almost wonder if I should be... In that case, do I even need to look at R equals 5? Well, no, I need to keep... Yeah. Like, he could be 7 or something. Yeah, I don't know if it's exactly fairy, but I think it should be something along these lines where I'm using intervals. And you always want to show that B and C are... Okay, I want to draw a bigger example. I think I understand this example. Here, if R equals 5 breaks, then I'd look at R equals 6. So let's draw a larger example with 0 over 1, 1 over 1, and we're looking for BCD. So 1/2, we already know that BCD are somewhere in here. And then I look at 1/3, 2/3. And let's say that they're still on the right sides. So B is on the left of 1/3, C is... Okay, so 1/4. Let's say things are still okay. So B... We could have like BB here. And then CB as shown. So 1 C D, and that will be okay because we get 3, 5, 6. And then the next thing that will check against B and C is 7 by fairy theory. Like the next fraction that appears is 2/7. So we want to say that D should be to the right of the 2/7 mark. Everything else before that is moot. 6/7 mark. And if not, and this something is wrong, for something to go wrong, that means B and C both round up, but D doesn't round up. So it's like 2/7. So like you would have B round up, C round up, but D doesn't round up. That would be the so-called bad case. And basically I think what's going to happen is that, yeah, now you look at 8 and you're in trouble. The next 8 fractions, there's no 8 fraction between 3/8 is out here. B can't cross it to make up for it. So I think if you just look at R plus 1, you'll die, basically. Yeah. 8, like 3/8, 6/8 is here, 7/8 is here. You're all on the wrong sides. So life is bad. And I think that should do it. Yeah, the first time B and C both round up, you look at the next fraction. And by FAREY theory, it's outside. You have no chance to round up any of them if you like don't follow the protocol or whatever. We are still on this problem? I think we just finished though. I think this should work. It's going to be annoying as heck to write up because I'm extensively using properties of FAREY fractions. But this should work. I'm like very confident this should work. Yeah, I think the claim is that I claim by induction that for every R, like B and one of B and C rounds up and then D always rounds up. And the proof is that if not, like if they, for example, if not, then you look at the first fraction for which it fails. Like for example, this 2/7, this 5/7, this 6/7. Then the next value of R will cause a contradiction because earlier decisions you made to get to, like this 1/3 blocks you from getting to the 3/8 is the TLDR. Yeah, I think it's a good problem, yeah. Are we done? I think we're done. I think I should just do it. I wonder what other people did? I don't know. I'm curious to see the official solution as well, actually. But I think this FAREY thing will... It's just the idea that you, like, as you give values of R, like, you keep narrowing into intervals. And then because you have some leeway for what B and C are, like, they can, you know, they kind of jump in either both, one goes left, the other goes right, or the one goes right, the other goes left. But you can't have B and C both go right, and basically you draw a diagram and see why can't they both go right. And the reason is then R plus 1 will cause a problem. Like you see here. How did you learn about FAREY sequences? I just kind of heard of them like 3 or 4 times and then eventually looked up things. I only know like about 2 properties of FAREY sequences, which is that... Okay, let me explain what FAREY sequences kind of are. Basically, we're going to start with 0 over 1. There's not very much to learn, I'll put it that way. So what we're going to do is you draw the fractions, right? The reason I was reminded of them is because that's basically what this problem was about. It's like, you know, you had these things that you wanted to see how they rounded, so... I don't know. Like, because of the way the floors in the problem were set up, it really felt to me like a FAREY situation. Okay, so basically you look at the fractions of denominator at most n. And there's exactly two properties that I know about this that I actually remember. One is that if I look at two adjacent fractions, the next fraction that will appear between them is like you add the numerators, so like this is 3 plus 2, and you add the denominators, so this is like 5 plus 3. So the next fraction to appear between these two guys will be 5/8. Moreover, if you take two adjacent fractions and look at the obvious determinant, it's like plus minus 1. Like 3 times 3 minus 2 times 5, or like this 1 times 3 minus 1 times 4, 2 times 2 minus 1 times 5. Yeah, that's like the only two things I know about this. But apparently this is true. And it really helps because in this problem, like I felt like the thing I was doing was trying to get B and C like in intervals, right? Each statement about R, depending on which way the thing's around, tells you B and C. It narrows down the interval they lie in. And I wanted to make sure they always go both left or both right or something like that. Or sorry, they never go both right. Yeah, they never both round up. Because the USAMO problem here, this 1999 problem, is equivalent to saying I keep splitting and then B and C can make a choice where they either go left, right, and then two of them have to go right, one of them has to go left. And the goal is to show D always goes right. And D always goes right because if B and C both go right, like they did in this example here, right, like if they both go right, then the next fraction will cause problems because you've already pinned it in such a narrow interval that R plus 1 will go out is outside your reach, and you cannot there's no way you can round right at all on the next turn. The end. Okay. That was a nice problem. I'm curious what the form solutions look like. Let's find out, shall we?